Welcome back. We're going to continue our discussion of amines. I think. Here we go. You may have thought I was going to skip this section, and then if that was your thoughts, then you'd be forgetting that when I introduced amines in chapter 1 of Organic Chemistry 1, I told you their most important property is that they act as bases. So we cannot ignore that as a section. It deserves our full attention. And we need to be able to understand the basicity of amines and put them in order. Right now, we know the pKa of ammonium ions is close to 10. We already knew that. That's what we memorized in chapter 4 when we did acids and pKa's. So all these numbers, not surprisingly, very close to 10. Please don't memorize these. But do ask yourself which one of these is the highest number, and that's this. That means it's the weakest acid. Of these 4, which would be the corresponding strongest base, would be that one. It has the lowest pKb. Where did these numbers come from? 14 minus 9.3 is 4.7. 14 minus 9.8 is 4.2, etc., etc. pKa of an acid plus pKb of the conjugate base equals 14. Here is the Kb reaction. It's reaction of a base with water. The base will deprotonate water. That's what bases do. They deprotonate species and they create hydroxide from the water and the conjugate acid of the base. There's the conjugate acid with a pKa close to 10. Now, my question over here is a good one. Why are secondary aliphatic? Oh, wow. Aliphatic is a word I don't use very often, but other chemists do. Aliphatic is just another way of saying saturated alkyl groups. And if you want a nice way to remember that, let's see. Fatty acids that are saturated. Those are the ones found in fats, by the way. It's just spell fat, P-H-A-T. Back in the day, that was a trend that I don't want to get into. But saturated alkyl groups are called aliphatic groups. And that's what these are. Methyls saturated. So these are all saturated. What do we got going on here? Why is this the best base is the question. And the answer is 2 parts. It's always going to be an interesting answer when the strongest of the 4 is not on either of the extremes of substitution or cation stability. Oh, these are cations. Can you remember what contributes to cation stability that you know from chapter 6 when we talked about carbocations? Why was a tertiary carbocation more stable than a secondary carbocation? Oh, it had more hyperconjugation. Do you think that changes with nitrogen? Answer, no. So in terms of hyperconjugation, that's the most stable carbocation, which means this thing should be the most easily made cation, which means that should have been the strongest base. But hyperconjugation is only half of the story. These species are also stabilized by the fact that this reaction is done not only with water as a reactant, but water as the solvent. So we've got to look at factors where the solvent stabilizes things as well. And water will stabilize any N with bonds to H by hydrogen bonding. And this species here has 2 H's that can hydrogen bond with water, which I showed here. This one only has 1. That's less hydrogen bonding with water. So even though it's got better hyperconjugation, it has less hydrogen bonding, and the overall effect is it's easier to make this cation. Similarly, this one has more hydrogen bonding than this one with water, yet it only has 1 methyl for hyperconjugation. So this has the best combination of hyperconjugation with the 2 groups and hydrogen bonding with these 2 hydrogens. This one has the best hydrogen bonding, but absolutely no hyperconjugation. So that one's the hardest cation to make, which means this is the weakest base. The numbers verify that, don't they? So we have 2 effects going in opposite directions. The hydrogen bonding stabilizes the species with more H's, and the hyperconjugation stabilizes the species with more carbon groups. This one has the happy medium of both. That's the answer to the question. So on your test, I'll have, I guarantee, either a primary versus a secondary or a secondary versus a tertiary. And I want you to show me that you know the secondary is a little bit better as a base than the primary or the tertiary. I won't have you compare primaries and tertiaries. It'll be a secondary with one of the other 2. Just telling you. Trying to help. Okay, now we get into other amines and the ones that are heterocycles. Question number 1, is this a better base with a pKb of 7 than these? And the answer is no, it's a lot worse. Well, remember, this is a powers of 10 scale with a P in front. And this is about 3 higher than those, which means it's about 1,000 times less basic. And why? Why would it be so much less basic? It must mean this is a lot less stable as a cation than any of those. True. Why? Well, you're taking a nitrogen that used to be sp2, still sp2 when you're done. sp2, here it's sp2 because it has 2 sigma bonds and a lone pair. There's your lone pair. And here it's sp2 because it has 3 sigma bonds, which is 33% S. 33% S is going to bring the cation closer to the nucleus than any of these nitrogens, which are all sp3. sp3 up here. And sp3 is only 25% S, so that cation is not brought in as close to the nucleus. Remember, the higher percentage S, the more things are sucked close to the nucleus. So I don't like bringing a plus close to the nucleus ever. Nucleus has plus in it. There's plus repulsion if you bring it closer. So that's the main reason why all of the things below are nowhere near as good as the things above. Good. So what do we got so far? Alkylamines are the best bases. Aromatic amines with heterocycles, not quite as good because, you know, these are sp2. Same story for pyridine. Now the question is, why is pyridine not quite as good a base as imidazole? That's one of our new guys right there. And the answer is pretty simple. These are stabilized by resonance with the lone pair on the other nitrogen, and there is no other nitrogen to stabilize this cation. Here we have 2 equally stable cations with the imidazole down here, right? And we can't do that over here. We just got the normal aromatic resonance here, just like we had up here, but spreading the cation between 2 nitrogens is a lot better. And yeah, it's not a huge effect, but it's substantial. And the worst bases on this page are the anilines. I've only got one aniline. Why? It's sp3. It should be like the ones on the top of the page. It should be a great base. Well, aniline has a lone pair. And that lone pair, as we learned in chapter 22, This is called an activating group towards electrophilic aromatic substitution. Why? Because the lone pair can resonate into the benzene. Can we have that same resonance stabilization of the lone pair here? No, you can't. There's no lone pair. You can't resonate this with the benzene at all. You've lost resonance. All this resonance down here is lost if you put a proton on the nitrogen. So anytime you do a reaction where you lose a lot of resonance, that's never a good thing, right? So the anilines are our worst bases. So let's do, we got a few minutes here. Let's do some comparisons. A quick one. We don't have a lot of time. Let's do the thing I promised, including something not on this page. We got that one versus this one. Ooh. Versus this one. Ooh, my pen's off? No. I want them all to be 5s. Versus, let's just say, this one here. I think we only have time for that. Go Roman numerals. And you know I like this question, putting these in order of weakest base to strongest. That's what I want to do. We didn't even talk about this one. If I had to put this on this page at all, and there's a reason it's not on the page. It's called parole. And not only does this nitrogen have to be sp2 to hybridize with the, to resonate with the other pi electrons, that lone pair is absolutely essential for what we call aromaticity. If you put a proton on here, it's not aromatic. And that's just going to be a quick, simple explanation of why 2 is the absolute worst base on this page. Lone pair is needed for aromaticity. You shouldn't be using it to pick up a proton. And there's no aniline on this page. But I got this guy that's very similar to this guy. Which one's better? I'm going to make a cation here versus making a cation here. They both have the same argument here. Lone pair is needed for aromaticity, but the one on the right is a little worse than this one, because if you put a cation here, you remember the nitro has a cation on the nitrogen there. That's even worse. Now I got cation repulsions. Cation repulsions in conj acid. Sorry, we're going a little fast here. And then the thing I promised that would happen on your test, you have to tell me 3 is not quite as good as 1, and I need to hear the magic words. In 1, I need you to talk to me about the conjugate acid, and I need you to say has the best combination of hyperconjugation, because it's got 2 carbons attached, and hydrogen bonding with the 2 hydrogens attached. It's got the magic words there. And I think that's a perfect spot to stop, especially since we're almost out of time. And yes, we're going to finish chapter 23 in the first hour of our next lecture. And that's going to be Monday. Wednesday is a week from test day. So we're going to have a day and a half of review. So get review questions ready and email me them this weekend. And there we're going to have review starting next day. And I will see you next week. Adios.